All right. Well, thanks everyone for coming to attend the Thursday session of the Ontario Public Works Association Public Works Week. We thank everyone for your attendance. A couple of quick housekeeping items. We do have 3 presentations for you guys today. There will be a question and answer period at the end of each question. There is a question box that you can access, or a question button that you can access at the bottom of the Zoom screen. So feel free to put your questions in throughout the presentation, and then we'll do our best to respond to them following that session. Without further ado, we can quickly move on to our first set of speakers. So the first presentation today is going to look into a water main condition assessment, specifically the backbone water main condition assessment program at the City of Ottawa. The presentation will be by Jared McGrath. He's an engineering technologist with over 10 years of experience at the City of Ottawa. His focus has been in the water and sewer field, beginning with the waste collections, and then moving on to lateral rehabilitation and grants program, and is currently with the linear condition assessment group. He's also leading a temporary service investigation project to plan future water main condition assessments over the next several years. So with that, I will stop sharing my screen and switch over.
Morning, everybody. Get the presentation up here. Right on. Yeah, so thanks for having me today. And I'm here to talk about the Backbone Water Main Condition Assessment Program at the City of Ottawa. And I'm work for the Public Works Environmental Services Department. And just to note, all the pictures that I'm showing you today are actual pipes and or work that we were doing in the City of Ottawa. So these were 3 breaks that we had on the backbone mains in the city. So today I'm going to talk about the distribution system in the City of Ottawa, and then what is PCCP, our program and our program priorities, the tools we use to carry out their inspections. I'm going to talk about our leak detection inspections and tools, our EM inspections and tools, give you a summary of what we completed in 2020, and then answer any questions you guys might have. So the City of Ottawa has 2 water treatment plants, 32 pumping stations, 14 reservoirs, and 6 municipal well systems. The entire distribution system is over 3,700 kilometers in length and is made up of several different materials. Our group's primary concern is the backbone transmission mains, which are larger than 610 millimeters in diameter, and that's what's shown on this map here. So there are approximately 235 kilometers of backbone transmission mains in the city, of which about 200 kilometers of that is pre-stressed concrete cylinder pipe, or PCCP. So what is PCCP? It's pre-stressed concrete cylinder pipe, and it's manufactured in accordance with American Water Works C301 standard. They started making this stuff in 1942. It's a complex composite pipe structure made up of an inner concrete core, a steel cylinder, pre-stressing wires wrapped around that, and then mortar coating on the outside to protect the wires in the steel cylinder. So the concrete core is the structural load-bearing portion of the pipe. The steel cylinder creates a water barrier between the concrete layers. The wire wrap compresses the structure to withstand the internal pressure, and then the mortar coating protects the wires and cylinder from external corrosion. The pipe is designed to withstand internal pressures and external loads using different components of the structure. The pipe has built-in corrosion protection. The mortar coating creates a passive alkaline environment, which protects the steel cylinder, but eventually cracks develop in the mortar that allows the corrosion to occur. So the 1970s vintage of this pipe is of greatest concern to us because of how it was manufactured. And we have about 60 kilometers of this 1970s pipe in the city. Because the wire wraps in the pipe withstand the internal water pressure, it's a cumulative amount of wire breaks that eventually cause distress in this pipe, and enough distress can cause a failure. So this pipe rarely has issues, with only about 1.4% of all the pipes tested showing signs of distress, and about 4% of the 1970s pipes tested showing signs of distress. However, when the pipe fails, it does so catastrophically. It'll sometimes leak at the joints, but the barrel of pipe will normally burst in a catastrophic failure. So this is a cross section of PCCP pipe. There's two different kinds as defined by C301. They're line cylinder pipe, which is shown in this picture, and embedded cylinder pipe. The difference is location of the wires. In line cylinder pipe, the wires directly touch the steel core, which is what you see here. Sorry, they touch the steel cylinder. And in embedded cylinder pipe, the wires have a mortar layer between the wires and the steel cylinder. So this shows a cross section of line cylinder pipe, and you can see this is the concrete core, this is the steel cylinder, these are the pre-stressing wires, and then this is the mortar coating on the outside. So this is a teardown of embedded cylinder pipe that was done a few years ago for a tool calibration at the city. And you can see the different parts of the mortar coating, the wire wraps and steel cylinder, and how the wires in this case don't directly touch the steel cylinder. So the square cutout section right here, that's where they cut out the steel cylinder, just so you can see the inner concrete core inside of that. So this is a picture of a distressed PCCP that was removed from the ground. You can see evidence of corrosion in the wires and a couple broken wires on that, which is why it was changed. So condition assessment, why do we do it? It's not cost effective to replace entire pipelines when only a small fraction of the pipes have distress. However, the distressed pipes need to be found and replaced to prevent failures like this. Boom. So our program was established in 2012, and it's founded on a risk-based prioritization of pipelines. Our objective is to reduce the risk exposure by finding distressed pipes and preventing failures. So this is a picture of the Woodruff break in 2011, which was the second major break on this pipeline. The result was water restrictions for all of Barrhaven for the summer of 2011, while the 850-meter section of this 1220-millimeter backbone water main was replaced. This is some of that 1970s vintage of higher risk pipes. And now the remainder of this pipeline is continuously monitored with an acoustic fiber cable, which actually detected an issue this spring and resulted in a repair that was just completed to prevent another failure. So prioritizing pipelines, the entire system can't be continuously monitored like is done on Woodruff. It's just too expensive and not required. So the condition assessment program uses a risk-based decision framework where a risk score was assigned to each backbone transmission pipeline. In this case, the risk score is equal to the probability of failure times the consequence of failure. So this was developed as a means to prioritize pipeline condition assessment and focus on the pipes with a higher probability of failure and a higher risk of failure first. So there's two different types of tools we use at the city for PCCP condition assessment. The first type is leak detection, and the tools are the SmartBall and the Sahara. And the second type is electromagnetic inspection, or EM, and the tools are the Pure Robotics platform and the pipe diver. So all of these tools have been used at the city at one time or another, but because of the way that the system is built in Ottawa, we primarily use the SmartBall for leak detection and the Pure Robotics platform for EM inspections. However, the city standards have been updated so that new pipelines or any facility upgrades can more easily accommodate all inspection types. So condition assessment on a pipeline for us is considered completed after both the leak detection and the electromagnetic inspections have been completed. Leak detection tools are used to identify any imperfections in the pipe, either cracks, leaks, or air pockets. The acoustic sensors on the tools listen for sounds emitted from water escaping the pipe. The data collected is then analyzed with algorithms to identify the location of the leak and predict the size of the leak. And then the magnitude of the leak can be estimated by correlating the value of the acoustic signal with historical calibration data. Because these tools are listening for sounds, they can also detect leakage through normally closed valves or leakage outside of the inspection limits or even leakage in a parallel pipeline. So different devices are used depending on the different length and configuration of the pipeline. Both devices are propelled by moving water inside the pipe. The SmartBall rolls along the bottom of the pipe and the Sahara is propelled by a drag chute. So more on the SmartBall. The SmartBall is an untethered in-service device used for longer inspections. It's slightly negatively buoyant, so it sinks and rolls along the bottom of the pipe. The ball is propelled by water inside the pipe, and it requires 0.3 meters per second to 1 meter per second of flow. It requires an insertion location that is a minimum of 102 millimeter or 4-inch tap. The picture on the left here shows what the insertion claw looks like. And extraction of the ball requires a vertical 102 millimeter or 4-inch tap to use the net. And that's what's shown in the center and the right picture here. The net deployed inside the pipe looks like this. So they stick it in from the top, and then it pops open, catches the ball, and then it collapses as they pull it out. Alternatively, the ball can be pushed into a reservoir and extracted with a remote operated vehicle, or possibly a fire hydrant can be outfitted to push the ball out with flowing water. So the smart ball detects leaks that are a minimum of 6.5 liters per hour using acoustic sensors. More on the Sahara. So the Sahara tool has been used only a handful of times in Ottawa. It's a tethered in-service inspection tool with a live video feed. So when an acoustic anomaly is detected, the operator can stop the tool. The operator can stop the tool, review the anomaly, and pinpoint the location of the anomaly. The tool is neutrally buoyant, so it stays in the center of the pipeline and uses a drag chute and the flow of water to propel the device. Same as the smart ball, it requires 0.3 to 1 meter per section of flow, and it detects leaks at a minimum of 11 liters per hour, a little bit higher than the smart ball. One limitation of this device is it cannot go through butterfly valves, which limits the distance the device can be deployed because most of the backbone water mains in the city are controlled with butterfly valves. Also, insertion is through a minimum of a 50 millimeter vertical tap. And because of this, it's not typically used in Ottawa right now because we don't have concentrically mounted vertical insertion taps on our older pipelines. Our insertion taps are eccentrically mounted horizontal. But again, the standards have been updated so to allow for more of these types of inspections in the future by providing proper insertion taps. So this map shows all of the backbone water mains in the city, the same map I started with. And this shows the pipelines where leak detection have been completed in blue, and also the locations where repairs have been completed because of anomalies found by leak detection. So far, we've completed 36.1 kilometers of leak detection on the higher risk 1970s pipes and 96.2 kilometers of inspection on all backbone pipelines in the city. Electromagnetic or EM inspections. They use a magnetic field to detect broken pre-stressed wires in the barrel of the pipe. The device uses an exciter and a detector, both located on the tool. The exciter coil creates a magnetic field, which travels along the wires in the pipe and is recorded by the detector. If there are broken wires or a discontinuity in the circuit, this changes the signal levels of the magnetic field. And through interpretation of the signal, the location and a range of broken wires can be determined. So manufacturing defects, corrosion, soil conditions, installation issues, operational issues, or third-party damage can all cause problems and cause the wires to break. Since broken wire wraps in PCCP cause distress and can eventually lead to pipe failure, EM is a very important test to determine the likelihood of failure and assess the structural condition of this pipe. So the EM tools used in the city are the Pure Robotics platform, which is a tethered, self-propelled, out-of-service inspection tool, and the Pipe Diver, which is an untethered in-service inspection tool that's propelled by the water inside the pipe, similar to the Smart Ball and the Sahara. The EM tools both use magnetic field to detect wire breaks, and different devices are used depending on the length and configuration of the pipeline. So this is a picture of the Pipe Diver inspection from Ottawa South that we did in 2015, and just a picture of the Pure Robotics platform crawler on the left. So more on the Pure Robotics platform. It's a modular, multi-sensor, self-propelled crawler that combines CCTV with EM, and it can also include other sensors to map and profile a pipe. It requires the pipe to be out of service and fully drained. This means temporary services are installed for any buildings that are directly connected to the backbone water main, similar to how it's done for a water main replacement project. It's inserted through inspection plates and tethered to the control truck. It can travel up to 1.9 kilometers from the access point, but it cannot navigate smaller butterfly valves, tight bends, or steep grades. So the inspection distance is limited by the configuration of the pipeline. So these are pictures of the control truck and the tool insertion in 2018. And you can see the 3 different modular sections of the crawler in this picture. More on the pipe diver. The pipe diver is an in-service, free-swimming EM inspection tool. It has onboard CCTVs, but they're used to track tool progress through the pipe rather than to assess the condition of the pipe. It requires a minimum of a vertical 305 millimeter diameter tap for insertion and extraction. It can also be inserted or extracted through an open channel or an inspection plate or a reservoir, but the pipe has to be isolated and depressurized to do this, which defeats the purpose slightly of an in-service inspection. It's neutrally buoyant, it's untethered and propelled by the flow of the water inside the pipe, the same as the smart ball in the Sahara. It can also traverse bends in the pipe and butterfly valves, so it's useful for longer distance inspections. The flow required is 0.3 to 1 meter per second, same as the smart ball in Sahara. And again, this device isn't typically used in Ottawa right now because we don't have very many 305 millimeter vertical taps. But again, the standards have been updated to allow more of these inspections in the future. And this picture is of the Ottawa South extraction tube from 2015. And the chamber was custom built in this case, just to perform this inspection. So this map shows all the backbone water mains in the city in black, and the pipelines where EM has been completed in red, and the locations where repairs have been completed because of wire breaks. So this map also shows in yellow, the location of the acoustic fiber cable that's installed in the pipeline on Woodruff, which listens for wire breaks, and also the location of the repair that was just completed because of this. So far, we've completed 37.89 kilometers of EM inspections on the 1970s pipes and 48.4 kilometers of inspections on all backbone pipes. So what we finished in 2020. So for a smart ball, we did INIS between Belcourt and Trim, and there was 1 leak detected in the ductile iron section of this pipeline. There was about 5 kilometers of pipe inspected, and this inspection was innovative because the smart ball was extracted by flowing it out of a modified fire hydrant, and that's what you can see in the picture here. So they shut off the lateral valve for the fire hydrant. They took the fire hydrant apart, took the control valve out of it, turned it around 180 degrees so the main port was facing a field, and then put it back together. And we used this to flow water out so we could extract the ball. So for the Herdman and St. Laurent smart ball, there was no leaks or gas pockets detected in about 4 kilometers of pipe. There was 1 acoustic anomaly detected, but it was outside of the inspection area on the other side of a closed valve, and we're still investigating what the cause of that sound was. Finally, for the Eagleson smart ball between Robertson and Campo, there was no leaks or gas pockets detected in about 3 kilometers of pipe. There was 1 acoustic anomaly, which was confirmed to be a pressure zone valve that was not sealing properly and passing water. And this map shows where our 3 smart ball inspections were in 2020 as compared to all smart ball inspections on the pipes in the city. So you've got Innis in the east end, you got St. Laurent, Herdman in the center there, and in the west end you have Eagleson. So for the EM inspections this year, we did Ottawa South, which is basically the edge of the transitway from Caladar to south of Walkley. And out of the 342 pipes inspected, there was 2 pipe sticks that displayed EM anomalies consistent with wire breaks, ranging from 5 to 10 broken wires. And this is considered non-distressed. And there was 1 pipe with anomaly that did not indicate broken wire wraps, which we're still looking into. So that could be a repair that wasn't recorded or something like that. And for the Eagleson EM inspection from Tim Road to Campo, out of the 261 pipes inspected, there was 5 pipe sticks that display EM anomalies consistent with wire breaks. 3 of the pipes had 5 to 10, which is non-distressed. 1 pipe had 10 to 25, which is considered distressed, and 1 pipe had more than 25. So this translates to a distress rate of about 0.7%, which is lower than the average distress rate of the 1970s vintage of pipe at about 4%. And here's the two locations of the EM inspections. Again, Ottawa South, just off the Airport Parkway from Kelleher to Walkley, and Eagleson in the West End here. Thanks very much for listening today, and that's all I have. Are there any questions?
Oh, that was great. We do have a couple of questions here. So the first one is introduction of impurities a concern when using Smart Ball Sahara inspections?
So all of the tools that are inserted into the water main are given a real nice chlorine bath, and there's a disinfecting procedure for everything when you're touching the water main. So they have like perchlorate on site, and they're spraying perchlorate on everything as they're inserting it in. The tethers are they're constantly bathed in disinfecting solution as the tether is pushed into the pipe. And in the one picture of the EM crawler there for Bridalwood, when it's sitting on top of the tarp, the reason it's sitting on a tarp is because it's all been disinfected and cleaned, and it's on the tarp, so it stays clean before we put it into the pipe.
Another question, in terms of the 1970s era pipe, is there a correlation between the configuration of the pipe and the breaks? For example, have you noted if their presence of the mortar layer, separation of wires touching the steel, affects the number of breaks?
So the reason the 1970s pipes are more prone to failure is because the standards for producing the pipe was laxed in 1970s. They tried making the pipes cheaper and stronger. So they added more stuff to the steel, which made the tensile strength of the steel stronger, but it also made it more brittle. So it made the wires more prone to breaks that way. And then the concrete layers and the steel can layer were actually thinner on that era of pipe, which is why it's more prone to failure. So in the 1980s and later, they strengthened the standards for that, and the pipes are thicker and stronger from those eras. But the biggest thing is the brittleness of the wire wraps in the 1970s pipes.
And so was that sort of a North America wide phenomenon with the 70s pipes?
Yeah, it's all through Canada and the US.
I think you might have already answered this question about what pipe manufacturers done to improve it. But one of the questions follow on to that was, have we upgraded our specifications for the pipe material to reduce the breaks?
Yeah, so the standards were updated through the 1980s and 1990s to make the pipe stronger again.
Another question, you mentioned that the Smart Ball technology could hear leaks in adjacent pipes. Do you end up with false positives through the analysis?
We haven't found on our pipes. Like Pierre recently did a presentation to us of the work they did in 2020, and I think it was in England where they found an adjacent pipeline with a leak in it. I was just giving an overview of what the tool can actually do, but I believe any of the calibrations or tests that we've done have been accurate for the leaks that the Smart Ball has detected.
Okay. And I think that is all of the questions that we've received. So thank you very much. Excellent presentation.
Okay, thanks for having me.
Pass it back to you, Paul.
All right, thank you. Certainly was a very interesting presentation. I must admit, Jared, those were some alarming images at the start of the presentation of the pipe burst, but it's comforting to see the extensive measures being undertaken to monitor and diagnose some of the higher risk areas within the city of Ottawa. So for our next presentation, we're going to be going to the other side of the country on a similar theme of safety and speaking about some road safety improvements on the transportation side of things in Regina. So the presentation will be by James Sulphur and Jason Jardine with Parsons. Jim, or James, was the design lead for the Regina bypass during the construction and closeout phase and is currently the engineer undertaking engineering services during construction manager for the Southwest Calgary Ring Road project. He has over 20 years of design, construction, and project management experience and has worked with consultants, contractors, owners, delivering transportation infrastructure projects from mini to mega throughout Western Canada. Safety is integral to all aspects of Jim's work. Jason is a traffic engineer, lead and project manager at Parsons as well. He was the traffic engineer lead for the Regina bypass during the pursuit, design, and construction phases, and is currently deputy project manager for the Kicking Horse Canyon Phase 4 project. He has over 20 years of experience, including the design, build, pursuits for major projects, preparing project traffic management plans for design, build projects, and managing transportation and planning studies for a variety of public and private sector clients. Jason takes pride in integrating safety into the design of his project. So it sounds like we've got an excellent set of speakers, and I'll turn over the presentation to them now. Thank you.
Good morning, and thank you for the introduction. Our presentation today is the result of many efforts of many, and so I'd just like to recognize, first of all, the Ministry in Saskatchewan of Highways and Infrastructure, our partners in this design build venture, which was Parsons, Graham Construction, Vinci, and CarMax. We were the design builder team, and so of course this doesn't happen alone, and we'd be remiss not to recognize them. So we'll get started on the presentation. The Regina bypass has been in planning since the 80s, 90s. And we'll walk through, we're going to go through the timeline, the scope, and the area context. We'll talk about the project team, some of the issues to implementation of the project, traffic management during the construction of the project, elements of the completed bypass, and the significant safety results, which make all of this worthwhile. So we're going to focus on those things today. Planning began in the 90s. The drivers of the project were safety, and we'll get to that in a moment. Procurement began in 2013, contract execution in July of 2015. Really 2 years and change later, we opened up the first phase, which is the dark blue bypass east, and that was the rehabilitation of the Trans-Canada Highway. Phase 2 was completed and opened in October of 2019, and that began the 30-year operation and maintenance phase of the project. So the scope and area context of this endeavor, again, it's the Saskatchewan Ministry of Highways and Infrastructure. It was delivered through their financing arm of Sask Builds. The infrastructure itself was 240 highway lane kilometers, 12 interchanges, 55 new service road kilometers, and the twinning of Highway 6. Vehicles served per day averaged 11,500 to 25,000 vehicles. And some of that traffic was unique. I've never seen agricultural vehicles as large as we encountered in this project. Commuter traffic, of course, in Regina, it's not as extensive as what we'd see in Ontario, but it is there. Farm accesses directly to the highway, and large permitted tractor trailer combinations. And again, the project team that delivered this, the concessionaire contracted to the ministry was Regina Bypass Partners. We participated in both the concession and the design building team, and the design builder team is where we'll focus today. And that was again, what I mentioned earlier, Parsons, Graham Construction, Vinci, and CarMax. And the operation and maintenance team is now underway after we've completed our first year of warranty. So the highway's holding up well.
Just to provide some context, some of the issues that were being encountered on this corridor. This is the phase 1 section, the real priority section that was shown in the dark blue on the previous slide. These are just some excerpts of some news stories that were quite prominent as we were preparing the bid and leading up to the start of construction and design. So growth, an obvious one. These are on the outlying areas of Regina. The Trans-Canada served as the main access to and from these communities. They literally could not get in and out of their community without crossing the highway. lots of high-speed 90-degree angle collisions due to the at-grade stop-controlled intersection. So a real sense of urgency as we led into this, with a lot of challenges and a need to do this quickly and safely. So in order to do that, we really had, we controlled our own destiny in many ways. This wasn't a situation where we were waiting for funding or waiting for property or for a planning study to be completed. We had the contract. The quicker we could deliver this infrastructure, the better for us, but also for the community. So with that, we took some innovative approaches to managing traffic while we completed the work. We were able to get the owner and the community to buy in to a much more restrictive traffic detour on the condition that we could actually deliver the completed project more than a year earlier than planned. So what you see across the bottom here is the progression from 2015 when we started. You can see the service roads, the at-grade intersection with high-speed Trans-Canada traffic. And on the right, the newly finished Pilot Butte overpass. So that involved a mile-long detour, complete isolation of the work area, and completion of the overpass structure, and full-depth rehabilitation of the Trans-Canada Highway. So really compressing design, build, and rehabilitation work with an intensive 2 to 3 year period. We also made use of temporary traffic lights. The portable devices you see in the corner really helped to address some of the safety concerns while we did our work in close proximity to these intersections, and was really well received by the community. So as part of the permanent elements, we also introduced some new configurations to Saskatchewan. We created the first modern roundabouts at the Balgony interchange at Highway 46 here. Those were a first for Saskatchewan. We also implemented a diverging diamond interchange. It was the second in Canada and first in Saskatchewan. So really worked to educate the local community on how to properly drive these and help them understand the safety benefits of these configurations, including working with Saskatchewan drivers training to update their driver's handbook. Some other elements that were included that relate to safety that were included in our scope. We had traffic data collection systems, all part of the ITS or Intelligent Transportation System components of the scope. Camera monitoring, road weather information systems, so helping with our ongoing 30-year operations and maintenance scope, as well as weigh-in motion and license plate readers to help with inspection of heavy vehicles coming through the bypass area. So all of these technologies really help to reduce exposure. Obviously, doing truck inspection, weigh scales, doing it remotely with technology instead of in person really helps with the long-term safety aspects.
And so along the way, there were thousands of workers that were on the ground doing this work. There were over 8,800 project orientations completed for the life of the project. Those are prior to beginning work on the project. Over 5 million worker hours, which was incredible. That did not include totals for the ministry and their staff and any of the ancillary works completed by other companies. And a recordable injury frequency of 0.32, which is phenomenal. We were lucky, not lucky, I suppose there was intention enough in the safety program that this many worker hours were completed, and everybody went home at the end of the day. There were some injuries, but everyone recovered and is working or living today that worked on this project. So significant achievement by the team. One of the innovative safety items that we completed was our final engineering deliverable for this project was the updated topographical survey. So the owner had completed a aerial LiDAR surface prior to the works, and our requirement was to update it. We, instead of sending crews out for what we estimated would be about 68 days of collection and other activities adjacent to the roadway, we employed a mobile LiDAR mapper, which completed that work in a day. It was a long day, but it was completed in a day. And so again, contact hours adjacent to live traffic were significantly reduced. And the information that we gathered was magnitudes of orders of magnitude better than we would have by employing the survey crews traditionally.
So in this final slide really sums up, us achieving one of our key goals, which, was reinforced from the top down, from the project director all the way to everyone working on the job, which was, get the job done on schedule, but safety first. And this is a collision history we obtained from Saskatchewan Government Insurance. It's broken down into 3-year bins. On the left here is 3 years prior to the start of construction. For fatalities, we were averaging over a fatality a year on this corridor before we started the work. The second column here is during construction. So from November 2015 to 2018, normally in work zones, you can see often there's increases in collisions just because of the changing conditions. People aren't used to it. In this case, with the installation of some of the temporary traffic controls, reduction in work zone speeds, we actually had a reduction in collisions while we were accelerating the work. And then 2018, at this point, all of the at-grade intersections had been removed. That collision risk was eliminated entirely. As we say, it opened late March of 2018, more than a year in advance. And, you could arguably say that, if we were averaging over a collision a year, a fatal collision a year, it's quite possible that acceleration saved lives. So a really important goal achieved, and something that the team was very proud of. So just want to wrap up with a thank you to everyone for inviting us, and open to questions.
All right, thank you very much. One question is the trade-off of the delay for early completion, in terms of delay of travel for earlier completion. How did you engage with the community on this?
So it's a great question, one that comes up quite often when you're doing traffic staging. I think the community was in favor of it when we proposed controlling those intersections during construction. They all acknowledged that there'd be more delay in terms of getting to and from Regina, but they'd feel safer. And that was a big trade-off. We went to all the local councils, explained the concept, and got a pretty resounding buy-in. Yeah.
I am not seeing any other questions. I have to apologize. There were two more questions that came up on the previous presentation. I'm not sure whether it was bandwidth issues on my side or not. So I'll just hold a second to see if there are any more questions on this presentation. Those questions that came in late, I have responded, or actually Jared responded to them, and those answers are showing up in the Q&A format. Oh, actually, here's another one. What is a diverging diamond interchange?
Yeah, so a diverging diamond interchange, really similar to a diamond configuration. You have two crossover intersections on the north and the south side. Probably easier to show a drawing, but what it does is eliminate left turn conflicts at an interchange. A little bit hard to get people used to it, but once they do, it actually operates quite smoothly.
I think you had an image of that in one of your slides, right? You want to just pull that up and maybe show it to people?
Sure thing.
More than one person had that question, but
yeah, sure thing.
Not sure that we have those around here, actually. Or maybe we do.
Yeah, so what happens is as you're traveling north, there's actually a crossover. So you're driving on the opposite side of the road, and then you make your left-hand turn unimpeded. So there's two signalized intersections, one on the north, one on the south, and we actually crisscross the traffic at either side. So you'd be surprised how intuitive it actually is after you've used it a few times. There's overhead guide signs to move people through, and much less delay than a conventional diamond.
And I'm not seeing anything else in the chat or the Q&A. So I think with that, Robertson, will be passing it back to you. Thank you very much for the presentation.
All right, thank you. Very interesting to see the multifaceted kind of approach needed to improve safety there, just from the design configurations, the driver education, and technology elements that go into these type of projects. So thank you very much for that presentation. Our next presentation is, I guess, not halfway, but partway between Ottawa and Saskatchewan in Peterborough. It's going to be presented by Mark Bruner. He is a structural engineer and senior associate of R.V. Anderson Associates Limited, with over 13 years of experience in civil engineering projects in the water, wastewater, municipal, urban development, tunnels, and amusement park rides. So he's got experience with resource staff management, project management, business development, and structural analysis and modeling for rehabilitation of new and aging infrastructure. Some of the more interesting projects that he has worked on in the past includes the deputy project manager for the $400 million capital construction project going on in the city of Toronto for the Coxwell bypass tunnel, and also undertook structural design and drafting foundations for some of the gigantic roller coasters at Canada's Wonderland, including Leviathan. I used to share an office with Mark back in Toronto, and what fun fact is he's got the most organized and that I've ever seen someone have today. With that, I'll turn it over to you, Mark.
Don't hold it against me. Can everybody hear me okay? Rob, can you hear me?
Yeah, I can hear you fine.
Okay, perfect. Thank you. Thank you very much, Rob, and good afternoon, everyone. Why don't we just jump right in? So this is the rehabilitation of a 100-year-old reservoir in Peterborough. We're going to talk about the background of the reservoir, the condition assessment that was done when a leak event occurred, and then the short-term repairs, followed by the more long-term repairs. And kind of the goal here is to just help everyone understand a little bit better what happened, so that if something like this were to occur to you, you'd have, the tools to maybe assess it faster than we did at the time. All right, background. So the existing reservoir on site was constructed in the 1920s. And as you can see, they used the tools they had at the time, which included literal horsepower to move earth around. Shown here are some of the beautiful handmade formwork and scaffolding that was used for the roof. And the final reservoir shown at the top. Now this was it was buried at grade, so we don't have any concerns about the river on the left there. So there was no real groundwater issues, and the entire reservoir was covered with 2 feet of soil on the top, and the walls were backfilled all around the sides. Shown again here in green is the 1920s reservoir. Now Peterborough Utilities Commission, or PUC, they retained R.V. Anderson to design a new reservoir. This was in 2013. The new reservoir was to be built in 2015. As you can see, the site is pretty tight. Shown again with this aerial, we had to chamfer the new reservoir just to allow the road to continue around the corner here. Now, the contractor brought in to build the new reservoir was North American Construction Limited, or NAC. And while they were excavating the site for the new reservoir, there was a significant leak event. And in case you're wondering, we did put a gap between the reservoirs. We were concerned that the design kind of required there to be backfill. So we did make sure that there was a gap between it. And while we were excavating within that gap, or while NAC was excavating, the toe right at the bottom there, that's the toe of the existing reservoir. They didn't undermine it. They went right to the underside of the toe. That's where water started coming out. And over a weekend, it flooded the site of the new reservoir excavation. And they were just about to get started with rebar for the floor slab, so it was a bit of a mess. So what happened is PUC decided to drain the existing reservoir and initiate bypass operations so that we could get in there and take a look and see what happened. So RVA was on site already for the construction of the new reservoir, so we popped in to see what kind of temporary solutions we could employ just so they could start building the new one again. So looking at the existing reservoir, just to give you an idea what it looks like, there's a chlorine contact tank and a clear well. It's about 50 by 40 meters by 5 meters deep, so it's a decent sized reservoir. In typical operation, the water comes in to the influent chamber. It does the usual thing around the baffle curtains, pops over a weir, and then sits in the clear well. And when it needs to go, it leaves through the effluent chamber. And there is some bypass piping between the influent and effluent chamber, which ended up being used when they drained the reservoir, which ended up leaking from this south side shown here. So during the bypass operation, they just closed the gates and just ran straight past the reservoir, and where they were able to send the water elsewhere. But they didn't want to maintain this bypass operation for very long. This is increased storage, and the winter time was coming up soon, and there were thoughts that frazzle ice might have an impact on the intake. So they wanted to get this reservoir working again, at least make sure that there isn't a structural concern, build the new reservoir, and then come back later and fix this kind of with a proper long-term solution. So what did we find when we went in there? A few things. There was internal leaking. The reservoir just wasn't leaking outside, it was leaking into itself. So what does that mean? Well, during the bypass operation, when the chambers were full, there were a few locations where water was coming out of that chamber. I'm just going to point out one right now, but it was also leaking through this gate. But this corner here, if I show you a photo, that's a leak. That's not a little bit of water, and that caused quite a bit of standing water across the entire reservoir, which made it difficult to actually see the condition of the base slab in a few places. And what we thought here was when they built the new influent chamber and the bypass and the effluent chamber, that was like 70 years after the reservoir was built. So that interface between the new concrete and the old concrete probably didn't have a water stop. There might have been poor consolidation. Something was going wrong with that detail. And this is not the kind of thing where you can just do some crack injection and walk away. So this was going to be happening for the duration of our inspection and probably some of the short-term repairs. We also found floor cracks. Well, when you see a crack in a reservoir, it might just be a shrinkage crack. It might have autogenously healed. it's not obvious what is going on when you see a crack. But when you see a crack like we did, the cracks were visible through the small layer of alum sludge residue on the floor, which is typical in reservoirs. Some cracks we couldn't see because we couldn't really scrape all the stuff away, but the ones that we could see were substantial. You could fit your fingers in them and push as far as you can. So these were thought to be probably the source of the leakage out of the reservoir. And we'll get a little bit later to why we think those cracks formed. Another interesting type of crack and leakage was from the effluent chamber. So remember that the influent and the effluent and the bypass, that was all functioning while we were standing inside this empty reservoir. So there was water in here, and these were closed. They weren't open like that. We happened to find a crack on the floor just next to the effluent chamber, and it was leaking into the reservoir, not through the wall slab interface. It was coming up, bubbling up through that crack, and it was depositing a layer of silt inside the reservoir. So during normal operations, this is full and that's full, everything's full. So there's no mechanism for water to kind of come back and forth as balanced. But when there was no water on this side, it found a path. And what that said to us was, there's a network underneath the base slab that the water's finding to come back into the reservoir. So that led us to think, well, maybe the leakage out of the reservoir wasn't just through the wall slab interface. Maybe it was from underneath. And if that was the case, there was probably a network of voids under the base slab, which is a structural concern. And as you can see from our quick little map of the cracks during our initial condition assessment, there was about 360 linear meters of cracks, and that's not a small amount. And they were the kind that you could kind of fit your fingers in. And you might notice that the cracks are pretty straight and at somewhat regular intervals, which says that these are not really structural cracks in the sense that there hasn't been a failure of the base slab under normal operation. These are probably, or for sure, were historic construction joints. Because when you pour this, certainly in the 1920s, you don't have a pump, you're not dumping it all necessarily in one go. You might be using other means. And that means you pour them in panels. And when you pour them in panels, you're going to have a joint between them, subsequent pours. And if that joint isn't prepared properly, it's potentially a weak point. And in this case, they were. So we knew that the reservoir was sitting on clay, which is a very fine, dense material. So we know that it hadn't washed the entire base slab out. There were some voids that took some time to wash away, and we know that clay isn't super permeable. So we knew there was some stability issues that we had to look at. There was also deterioration, not just leaks and cracks. When the reservoir was built, they had jacketed some of the columns. And what that means is probably there was poor consolidation when they dumped the concrete from the top, and the paste stuck to the rebar and the aggregates went to the bottom. So that's fine. That wasn't deteriorated, but some of the columns, as you can see from here, didn't really have any paste in front of the aggregates. And that superficial paste is pretty important to kind of ensure that the rebar underneath has cover. So all the chemicals inside and the water that's in the reservoir doesn't immediately start attacking the rebar and causing it to corrode, which is a structural concern. In this case, the paste was gone. There were some chunks gone. You could see some of the rebar. So this was a structural concern. And of the 70 columns, about 10 of them look like this. The others look totally fine. So we kind of suspected this might have been a type of concrete issue, maybe the batch that was used for the columns they were all in a line, by the way, the 10 that were deteriorated. So maybe the concrete used that day, or if at that period of time didn't have chloride resistance or something. But that type of deterioration was present elsewhere. This is the influent chamber, also where they would dose some of the chemicals. So you could see the paste is almost totally removed. That doesn't mean the cover is totally compromised. It might only be, say, a 1/4 inch gone, and there might be another, say, few inches behind it before you hit rebar. But this is the type of thing where it might not be causing a leakage, but it would prevent this structure from lasting another full life cycle if nothing were done. So that's what we found in our condition assessment. So we wanted to make a few recommendations to PUC on short-term repairs such that you could reinstate this reservoir, recommission it, start using it, build the new one. And then once the new one is built, you can come back, take this reservoir down and start doing long-term repairs. So number one goal, preserve the structural integrity. We have to do that. Number one, reduce the leakage out of the reservoir. We can't have it continually leaking into the new excavation, and commission the new reservoir as soon as possible to get back on track with fixing the existing one. Time was of the essence here. Dewatering. So what do you do to dewater this? It's leaking into itself from the bypass, which they couldn't stop at the time. Well, I mean, it's pretty simple solution. It doesn't look pretty, but it works. You put some sandbags and polyethylene and a pump and bring that water to a low point. The reservoir had a sump. So it's not pretty, but it certainly captures the water. Same thing for the other crack, the crack that was leaking up into the reservoir. You kind of clean it off, put some sandbags and polyethylene and a sump pump. It's a cheap, simple solution. What about the cracks? So you remember this picture. Well, a quick and simple solution, which isn't really intended to last for a full life cycle of the reservoir, is to just do crack injection, polyurethane, a lot of polys. So what you do is you drill holes on either side of the crack, and typically you would do it staggered. And you drill the holes at an angle so that when you're pumping from the top, it reaches the bottom of the crack. Because if you drill kind of too close to the crack, you might chip the concrete away. In this case, we had the holes spaced at 6 inches. And the polyurethane, you put packers into the holes and then you inject it with polyurethane. But before that, you probably want to clean the crack out. So they use some high pressure wash to kind of clean the crack out. And this material, the polyurethane, it's an NSF approved material because this is, of course, a water reservoir. Everything has to be, drinking water quality approved. And what happens to the polyurethane is it reacts with the water and it expands. And as it expands, it fills all the little holes within that crack. And again, this is a temporary watertight seal. It's not intended to last forever. It was just to try and limit the water that was leaving the reservoir so they could continue building the new one. I've heard people say this would last for 3 to 5 years. I don't know if I'd ever provide a warranty to someone, but this is not a long-term solution. I will say, though, that the guys who did it were just exceptional. They could do 60 meters just in a day. So they got this done probably in 2 weeks. So you remember the image I sent earlier showing our kind of rough estimate of where the cracks were. Well, the next slide here, it shows what they actually ended up fixing. So the green lines are cracks that were injected with polyurethane. The blue lines, I'll get into that later. Those were previously unknown small cracks that we uncovered when we were doing the pressure grouting operation. So that's interesting. We'll talk about that in a bit. I guess we'll talk about it now. So the final step, remember how we talked about the structural stability being kind of the big concern. We wanted to make sure that all the voids underneath were filled. Well, one way to do that is pressure grouting, and it removes the need to just bust the entire floor up and cast a new one. So we're going to get into a lot of details about this because it's very interesting to me, and you may have to do this in the future. So let's learn some lessons from what we found. So when we did this work, it was during polar vortex, super, super cold outside. So we put the grout batching plant off the roof because the roof had limited load carrying capacities. And they had, I keep saying we, it was really NAC who was doing this. So NAC ended up constructing this nice little tent area with heaters. And the water source lines, again, everything that went into the batching had to be kind of kept at a certain temperature so it didn't freeze. Inside, there was a cool little mini batching plant. And it was very, very effective, of course, but it required constant supervision during operation. They had to make sure they were supplying enough grout and the grout had the right mix. And it satisfied a bunch of different types of tests for, viscosity and density to make sure that when it was pumped under the slab, it actually displaced the water that we suspected was underneath it, instead of just mixing with it and making a big mess. So the reservoir didn't have a lot of huge access hatches. There was one large hatch. but they were mostly small hatches. So everything that went in here had to go through those accesses, including all the lines and all the material. So the device that they put together here is pretty interesting. It was a little mini grouting apparatus, and this helped control the flow and the grout, among other things. And the guys down below had radios with the guy up top in the grout batching plant, and they could make sure that the right quantity was on its way. And a little schematic here to give you an idea what this looked like. So that the grout batching plant up top, there was a grout return line that continually cycled the grout to make sure it wasn't setting up and kind of solidifying in the line. So within the tank, there was a ball valve, flow meter, and a pressure transducer. That helped everybody kind of understand how much quantity was going in there. And we had limited the amount of pressure they could pump under the base slab. We kind of knew what the slab could take in terms of uplift pressure based on its design. Because if you put too much pressure in there, you could fail the slab structurally in bending in the direction it was kind of never really designed for. That slab is designed to take water pushing down on it, not bending like that. So when you look at the actual slab with the grout batching plant up top, they drill holes in the slab at a good, solid interval that we thought would, kind of made sense without turning it too much into Swiss cheese. And at some cases you'd grout and it would fill the hole and it would pop up an adjacent hole. That was a pretty clear indication that there's a void under there. So they would put a cork in the hole where the grout was coming up and keep pumping. Maybe it would pop out another hole, maybe it wouldn't, maybe the pressure would rise to a point that they had to stop, and then they would simply stop, which said to them that the void was filled. Another case, they'd fill a hole and immediately the pressure would spike and they'd say, okay, there's no void here. And in some cases they'd get a little bit of flow, but then that would be it. So that said to them, maybe there's a tiny void, maybe it's not connected to anything. So those were kind of the three little situations there that we would find. And just to give you an idea what that equipment looked like, this was the grout delivery hole and the grout line. I mean, I said we didn't want to make a mess, but we made a mess. It's really impossible to not. But this is all cementitious bentonite products, so it's not like it was a water quality issue. And of course, the reservoir was clean beforehand. And so anyway, just this is what I meant by a previous unknown crack. In some cases, they'd be pumping in one hole, and grout would simply come up from a place that nobody expected. And once we looked at it, we realized, oh yeah, this is a crack that was thinner for us to kind of notice, but in the limited way we could during the condition assessment when there was standing water. But it was clearly wide enough to allow grout to come up. So that was another type of fix we had to do. We had to come back and inject those as well. So this is a quick little animation to give you an idea of how we chased the voids underneath. The reason I'm showing in this location is because when the contractor came to do crack injection, he wasn't able to see the polyurethane come up. It wasn't foaming and reacting with the water and filling the crack. It was just getting lost. So we thought, well, if this crack here isn't able to get filled with polyurethane, there's probably a big void. So we use this section to kind of better understand how the grouting procedure might work in other areas. So as you might imagine, instead of just putting holes every, say, 5 meters at the joints, we put a lot of holes. And you start grouting, you pump grout from one of the holes to see where it went. And sometimes it would pop up a hole beyond, and okay, so we'd keep pumping from that hole and see where it went, and it'd pop up a crack, and we'd drill another hole beyond to see if the void extended even further in the direction it originally was. And maybe it did, maybe it didn't, and I'm not going to go through all the steps. I just want to show you kind of the progression and where we started pumping and where it flowed to and where it didn't. And at some point, we found a big section, and it just, the grout went absolutely everywhere. It went backwards, it went forwards, it went sideways. So eventually, and we're tracking the quantity, of course, and we're tracking the pressure that is being used to pump. And at some point, you just, can you guys still hear me? Sorry, I think I lost my headset.
Yeah,
Now we can hear you. Yeah.
Good.
Okay, sorry, my headset turned off. If that happens again, I'll plug it in. Sorry, guys. Anyway, maybe I should just speed up. So anyway, at some point we got to where we couldn't really pump any more grout. It wasn't flowing anywhere. No holes were taking grout, and we thought, well, we pretty much have a better understanding now of what this void looks like. So we kind of drew contour lines based on where the grout was taken and where it flowed to. And this gave us a pretty good idea of how to chase it, the kinds of pressures and flows we might be getting, and the kinds of numbers of holes we thought we might need to determine where the voids were. And I said we didn't want to turn it into Swiss cheese, but we did. There was really no other way to chase the voids. And people will say, well, you could have dragged a big heavy chain along the slab. You could have done some kind of radar. Yes, you could, but that wouldn't have solved the issue of actually filling the void. So we figured we would chase and fill simultaneously. And this shows what the voids look like, with the shallow voids taking just a little bit, the medium taking more, and the deep voids taking a lot. So the south side of the reservoir, which was right here where the water kind of punched out into the excavation, it shows a big red patch, right? So that indicates that not only were there cracks there leaking below the slab, but it kind of connected to the side of the wall, and that's kind of where it punched out. And I should say we pumped about 11 cubic meters of grout under the slab. And if you take the area by all of these, voids that we tracked, it's, I think it was 6 inches or 8 inches of concrete. So it really had carved quite a network of voids underneath. So now that the short-term repairs were actually complete, the existing reservoir was under control. It could be recommissioned. We didn't have a structural concern with it anymore. There may still be some leaks here and there, but not to the degree that they would stop construction. So NAC ended up building the new reservoir, and it looks great. It was commissioned. It ended up working totally fine. And now we could jump back in and do long-term repairs. So what were the goals of the long-term repairs? Extending the service life. This was 100 years old. And honestly, with the exception of some of the issues I pointed out earlier, it was in exceptional condition. There's no reason that they couldn't continue to be used for another service life. So we wanted to do that. And we wanted to waterproof the interior properly, not just with some crack injection here and there. We wanted to do a real thorough waterproofing. And then the concrete rehabilitation. You remember how there were some pretty serious deterioration issues. So looking at the deterioration, the columns that had the paste kind of fully removed and chips in them, we designed full height jackets. So you may recall earlier there were some jackets that only came up to maybe your waist. Well, the columns that needed full height jackets needed full height jackets. And we designed it with 175 millimeter thick steel reinforced concrete. We used a type of mix that's called CXL, which is an exposure class that helps resist future chemical attacks that are likely to be used in the tank. And the strength was 50 MPa at 56 days. One of the reasons that mix was chosen is because it's not super easy to get concrete in here inside of a tank unless you want to drill a bunch of holes in the ceiling and drop it from above. So it was actually pumped from below. There's a port here and a port there and another port elsewhere. So it was it's self-consolidating concrete. They didn't have to be vibrated. You just pump it from below, make sure the air is getting out, and it ended up looking like this on the right. Pretty darn good looking. And the walls, you may recall earlier in the influent chamber, I showed you just the walls looked like all the paste had been removed. So the first step was to just clean the walls, clean all the concrete surfaces with a high pressure wash so we can actually apply new materials and they're not just going to delaminate because of the material that's already on the walls. And in this case, we specified 7,000 PSI pressure washing, which might sound like it could cut a car in half. That's really super high pressure, but this is 100-year-old concrete. It's extraordinarily strong. It took it like a champ. The nozzle here was super fine and there was no problems whatsoever. Maybe the aggregate or two would pop off every now and then because it was already falling off. But the concrete surface was ultimately cleaned very, very well. And you can see here kind of before and after of one section. A really noticeable piece was a historic parging that was done on the walls when it was built, probably due again to poor consolidation for whatever reason in that area. So, and that stood up totally fine. There was no deterioration of the concrete there, which suggests that it was kind of a different mix than the walls when they were originally poured. And this shows kind of the progression of the solution to reinstate the walls. On the left, of course, is the concrete after the pressure wash. And this was just a mock-up that was done in the reservoir, so everybody understood what they were going to do everywhere. So step one was just a primer coat. This is just to make sure that everything adheres okay. Step 2 was troweling on a parging coat. So what that does is it actually reinstates the wall thickness to what it originally was. And that product there happened to have crystalline waterproofing properties, so that would get kind of embedded back into the existing concrete to kind of give a bit of belt and suspenders. And then step 3 was actually applying a proper waterproofing coat over the entire original parging layer. And this product, they were all by a company called WR Meadows. The first one, product number 2, was a Semcoat CW+, and 3 was called Semcoat Flex ST. There's a lot of products on the market. We use Sikatop 1, 2, 3 elsewhere in the tank for the columns. So there's lots of products that have really good performance for these types of applications. And this just gives you an idea of what that parging layer looks like. And this shows what it looked like when it was done. It's surprisingly smooth finish. And smooth is desirable for a reservoir. The less surface area, that means less potential bacteria accumulation. And this shows some of the columns that weren't too badly deteriorated. They just needed a bit of a thin troweled coat of a cementitious product. And like I said, we use the Sikatop 1, 2, 3 here. And waterproofing isn't really required on the columns. It doesn't really matter so much if water gets from one side or the other to the column. So we didn't specify that. And you remember a while ago I said how when you pour a base slab, you want to do it in panels. If you pour it all in one go, you're sometimes going to be susceptible to shrinkage cracks, and shrinkage cracks can get bigger and deeper as time progresses. So you do it in sections just big enough that it allows it to shrink a little bit. And then when you pour the next section, that kind of closes the gap here. And you may notice on the floor here, every single crack that we had previously injected with polyurethane, we had dowels drilled in with a few bars going parallel to the cracks, and that would hold this new concrete topping. We figured instead of ripping out the base slab and pouring a new base slab, just leave the base slab in place. Most of it was okay. And most of these cracks with the polyurethane weren't going to stay for too long. So we just put a new topping slab in there as a waterproofing layer. The walls were in good enough condition and they weren't leaking at all. There weren't cracks in the walls, but the cracks in the floor demanded a bit of more robust waterproofing layer. And in this case, we're not talking about a 1-inch, 2-inch waterproofing layer. I believe the layer was 200 millimeters, and it was fiber reinforced. It was pretty hard to get, or we thought it would be pretty hard to get massive panels of welded wire mesh or just conventional steel rebar down here. That was just not really feasible. So we opted for a fiber reinforced slab. And I don't know if you can see it very well here, but you can see all these tiny little fibers in the mix. And they just come in massive bags, and you just dump the bag in the concrete truck, either at the batching plant or on site. And you make sure that the amount of bags you put in is to be the correct dosage that you need. And in this case, we dosed it with 35 kilograms per cubic meter, which is a very robust amount of fibers. And the purpose of these fibers, the macro fibers, is for crack control. They get randomly distributed in the slab in all directions in all ways. And when there happens to be any kind of shrinkage or any kind of flexural movement, it really, really holds the concrete together. I'll show you a little bit what it looks like when it's finishing. Some people, the contractor, the client, were worried that there'd be a hairy slab. Everything would be standing up like this, and that might lead to corrosion of the fibers, which would then extend into the slab. That's not really the case. The fibers were made of steel. They're pretty dense. They don't really rise to the top. And certainly when it's finished, in this case with a magnesium steel trowel to prevent sticking, they just get pushed down. If you've ever been into an IKEA in Toronto, you'll see that their base slabs also have fibers, although you can definitely see them at the surface. In this case, they were not visible at the surface because it was finished so well. And that ends up being what it looked like. And I walked the whole slab. I did a bit of a condition assessment to see how well it performed. I couldn't find a single crack, maybe one minor hairline crack here or there. And at least the ACI, the American Concrete Institute, when they talk about fiber reinforced concrete, the many benefits of it is even if there is a shrinkage crack at the surface, due to the nature of the density and the randomly distributed fibers, that crack's only going to extend a few millimeters down, if that, and then it's not really going to go anywhere. So this gave a superior smooth finish, which is what we want in a reservoir. No visible shrinkage cracks, and any cracks that were in the floor below, are now held in place by this new floor topping. So, the overall construction budget here was 2.9 million, which was about a third of the cost to demolish and build a new tank. And with this fully rehabilitated reservoir, it's probably going to remain operable for another full life cycle, which is pretty good value for a third of the cost. And earlier, or I guess about a year after this was done, it was recognized with an award by OPWA for in the category of structures, and we were like really happy to receive that, because we kind of learned as we went, and we tried to address it as best we could with the short and long term, and it was nice to get recognition, and certainly Peterborough Utilities was very happy as well. So it ended up being a very successful project. So we did the assessment of the existing reservoir in a very time crunch kind of nature while they were trying to build the new one, and we did the short and long term purely for the needs of this project. You may want to go straight to long term if you see this kind of issue, and we were able to actually extend the service life of this 100-year-old tank, and hopefully it'll last another 100 years. I hope I didn't go over my time. I think I went a little long, but I really do appreciate everyone listening, and if you have any questions, I'd be very happy to answer them to the best of my ability.
Perfect timing, actually. We've got time for a couple of questions, and there are a couple of questions posted. So thank you very much for that. Really interesting. Oh, and more questions coming through. Please get your questions in now, because there does seem to be a little bit of a lag in them showing up on the screen. The first question is, did you have a delay claim from the general contractor for construction of the new reservoir when you knew short-term repairs had to be undertaken in the existing reservoir? And how much additional cost did that add to the capital project? What lessons did you learn?
Yeah, so I'm a structural engineer by nature. I wasn't the PM for this project, so I would be guessing if I gave a number for the delay claims. The actual cost to do these short-term and long-term repairs was its own thing, the 2.9. If there were any additional costs from the contractor due to kind of shutting down at least the base slab pouring, I wouldn't really know how much that was, but that was all kind of resolved. The contractor on site ended up performing all of the short and long-term repairs anyway, so kind of all canceled out, but don't hold me to that.
Another question is, was there a concern that you could lose grout into the adjacent river, and how did you manage that risk without knowing the volume of grout that you needed?
That's a really good question. I've never received that question before, so let me struggle to answer it. The river was really far away. I'd say it was probably about 100 meters, and we didn't know. We didn't know if the voids connected to the river. I would say that we were pretty high up, so if it were to connect there, it would not only have to travel horizontally, but quite a bit down. And once the outlet to the new excavation was kind of unearthed, and it had a very simple path to go to, we had simply kind of assumed that the grout would kind of travel there first before it went to the river, and not sure if that was the case, but I would say that when we were doing all of the pumping underneath the slab, we didn't see any pump out through the side, and every time we pumped, we saw water come up into the tank from the other holes, which kind of said to us that we were not only displacing the water, but we were not, taking the path into the excavation. So it's possible. I'm not sure, but the amount of concrete that we ended up pumping into there, the 11 cubic meters, like I said, it was about 200 millimeters uniformly if you take an average for the area that we ended up pumping, and that sounded about right. If it was more 10, 20, 30, 40 cubic meters of grow, I would have had an extreme doubt that we were we were not connecting somewhere.
Going somewhere, right?
Yeah, it sounded like the right number to me, and this is kind of a gut check thing. I'm not sure there's any technical basis for that.
There are a couple more quick questions that have come in. I know we're getting at time. I'll just throw them out there if you can answer them super fast. Did you put a sealant coat on the new slab, and did you put rebar dowels and or keyed joint along the joints of the panels that you poured on top of the slab?
Yeah, great questions. So the sealant coat, no. The topping that we put on there, the 200 millimeters, it is the sealant coat, if you will. It's a very elaborate waterproofing coat. It's a 200 thick waterproofing coat. So we had kind of determined that with the fiber reinforced nature of it, it would be sufficient without an additional waterproofing layer. And in terms of the rebar dowels or a keyed joint along the joint, yes, we did. this is typically an hour-long presentation where I show lots and lots of very detailed photos and cross sections of everything. I didn't have time for that, unfortunately, but every single time there was an interface between the new concrete in the floor slab and the existing concrete, whether it be the wall or a column or anything like that, we made sure there was a keyed joint that had a water stop and rebar. And you know, you can never perfectly keep water in anywhere. It'll always find some path somewhere, but every single interface between new and old, we did the best we could to specify that joint properly and to kind of ensure that we're not, that any shrinkage that might occur wouldn't kind of make that a weak joint again.
That is all of the questions that I am seeing in the chat. So I'm going to pass it back over to Rob.
Great questions. Thank you so much.
All right, thanks again. That's certainly an interesting presentation. It's always interesting to see where the kind of the path of least resistance isn't taken in terms of sometimes it's easier just to say, you know, demolish it all and you know, construct new, but oftentimes there is that value in taking the time to assess it and figure out how you can rehabilitate structures. So that does conclude our set of 3 presentations today. There are a few more presentations in the afternoon that are part of the CPWA and National Public Work Week that can be accessed through the website. I think there's still time for those that want to join for a 2 p.m. session on some of the basement flooding program and flood risk mitigation that's going to be undertaken in the city of Toronto. All the webinar sessions or the presentations during this week have been recorded, so those should be available from the website probably in the coming days or so. And I would just like to note that kind of on behalf of the Ottawa Valley chapter for the CPWA, we will make a donation to the local food bank here for a thank you on the presentation. So with that, I'll sign off for the day. Enjoy the afternoons, and thank you for attending, everyone.
Thank you so much.
Thank you.